Hello friends, so today just we are going to see the different kind of that phases in the phase diagrams. So in the last lecture that we have completed about the lever arm principle, and now in this particular lecture we are just going to see what are the different kind of that phases are present in the equilibrium diagram. So these phases are very much important to understand the FE3C diagram, because this is the basic of Fe3C diagram, that is the iron and carbon diagram. So before going for that iron and carbon diagram, what are the different kind of that systems are there that we are just going to see, and then we will just go with the iron carbon diagram. So in the next lecture we will just go with the iron carbon diagram, or some few stages are remaining. So after two lectures we will just go for that iron carbon diagram. Right now in the next two lectures we will see the different kind of that phases which is very much important to understand for the iron and carbon diagram. Now the first condition, that is the two metals completely soluble in the liquid and solid states, that is called as an isomorphous system. So basically when we are mixing the two metals, what condition that we have seen in the previous lecture. So the first condition, if the two metals, what are the different stages of the any kind of that alloy? That three stages are there. What are those three stages? One is the liquid stage, second is the solid plus liquid stage, and third is the liquid state. So those two metals should be soluble in both the stages, that is liquid and solid. Means when both the metals are in the liquid state, that has to be soluble in each other. It should not be there one metal is in the liquid state and second will be remains as in the solid phase. It should not be happen. So both the metals should be completely soluble in the liquid as well as in the solid, because it should not be separate out in the solid state. So when we are just cooling down the any liquid state, that has to be converted into the solid state that we are knowing, but in the solid state it should not be gets out separate, so it should be remains present in the single solid. So that is the solubility in the solid state. So a system that illustrates an equilibrium diagram in which there is a complete solubility in the liquid and solid state is that of antimony and bismuth system. So right now we have taken all the examples about the antimony and bismuth, and that's why we will just continue with the same example for the further lectures. So there are few examples of such kind of that systems are there, that is the nickel chromium, that is NiCu, AuAg, that chromium and molybdenum and WMO. So these are the such kind of that examples of alloy, so which is completely soluble in the liquid as well as solid state. So any example you can be able to take for this. We have taken the example of antimony and bismuth, that is Bi and Sb. So since the two metals, that is Sb and Bi, or nickel and chromium, are completely soluble in the solid state, and the only type of solid phase form will be the substitutional solid solution. So this is when it is completely in the solid state, it will be a substitutional solid solution. The equilibrium diagram consists of two lines only, that is the liquid and solidus. So whatever the equilibrium diagram is there, that will be only contains the two line separate out, that is the liquid as well as the solid. That is what are the two those phases are there. In the next slide we will see that what is the liquidus and solidus slide. The equilibrium, whatever will be the diagram, that will be contains the solidus and liquidus stage for Sb and Bi. So above the liquidus there are uniform liquid solution for any alloy in the series, while below the solidus there is a single solid solution of any alloy. This is very much important. Single solid solution means those two materials will not be separate out in the solid state, that will be remains mixed. Only single solid solution will be obtained below the solidus line. So between the liquidus and solidus, both liquid and solid solution coexist. So whatever may be the middle condition it is there, that is the we are saying that equilibrium, that loop, it is there. So inside that particular loop, both the solutions are there, it is the liquidus and solidus. So this is the diagram. Again, we will just hurriedly see that which kind of that conditions are there, and then we will just explain this diagram, and then we will go for the second condition. So here, this is when we are mixing the bismuth and antimony. So this is the percentage of bismuth, this is the percentage of antimony, and this is the liquid phase, and below this will be the solid phase. So here we can be able to observe it. So liquid and solid. So whatever may be this curve or loop we are getting, above this particular loop, everything will be in the liquid state, and below this particular loop, everything will be the solid state. And this particular curve is called as liquidus. This particular curve is called as a solidus. So you just understand this. And whatever may be the remains present in between these two lines, that is the solidus and liquidus, it will be in the both condition, that is the liquid and solid. Now this particular diagram we have intersected with one line, that is 1A to L. This line we have drawn, and we have plot the 2-3 points on this, that is for the 1200 degrees Celsius first point it is there, for 900 degrees Celsius second point it is there, for 600 degrees Celsius third point it is there. Okay, and the horizontal line for the 900 degree temperature 900 degrees Celsius temperature, and that is intersecting to this particular loop at 2 points, that is O and P. And what intersecting line, vertical line we have drawn, it is intersected at point M. So OMP, it is just a horizontal line at 900 degree Celsius temperature. Now consider an alloy containing the 30% bismuth and 70% antimony. So we have just intersected with the 30% bismuth and 70% antimony. As the liquid alloy cools, the freeze start at about 108 degree Fahrenheit, that is 582 degrees Celsius. So this is the temperature range in the Fahrenheit, degree Fahrenheit. So 1080. So where is 1080? We can be able to see here might be that 1080 degree temperature, whatever may be the S point we are obtaining. So here the liquid alloy cools and freezing start at 1080. So freezing start means just it has been starting to convert into the solid state. So when this will be the composition, that is the 3070 is the composition, at 1080 the freezing will be start, means liquid is starting to convert into the solid. It is not 100% converted into the solid, but it just start the transformation from liquid to solid. So when we are talking about any composition, at the different temperature ranges, we are just getting the different kind of that stages. Means if we change the composition, that is 4060, okay. So 4060 might be we are getting the different temperature of freezing. So for the 4060 it might be below 1100. So near about 1002, likewise we will get it. Okay, 1020. So the composition of solid form and liquid at any point, say 2m, can be found from the equilibrium diagram as explained under the section. So the composition of the solid form and liquid at any point in the sense, suppose at point 2, whatever may be the composition, okay, on the equilibrium diagram, that we can be able to sort out. So as cooling continues, the stage, that is point N, reaches when the whole mass. Now just consider about that point N. So what is the different phase S to N? So at N, whatever maybe we are getting, that whole mass is solid, and further cooling will be brought to the solid to the room temperature. Now from 1 to S, we will just explain about that particular diagram. So from 1 to S, the alloy is in the liquid state and no changes occurs. So from point 1 to S, there is no any change. Okay. So from 1 to S, whatever may be the alloy, that is bismuth and antimony alloy, that is present in the liquid state only. So when we are just dropping out the temperature, that is 1200, okay, so at point 1 the temperature is at 1200, and when we are dropping that temperature from 1200 to 1080, means almost we have dropped out the temperature by the 120 degree Fahrenheit. So that when we are dropping the temperature at 120 degree Fahrenheit, the stages will not be changed, means only the liquid state will be present, but at point S it is just start freezing now. Now at just below S the solidification start and solid phase separate out from the liquid. Okay, so just below S the solidification will be started, and now both the phases will be trying to separate out, means solid as well as that liquid will be try to separate. The amount of solid increases, this continues up to n, where the last liquid freezes to solid. So whatever may be the amount of solidification, that's in the solidification stage, the amount of liquid is decreasing and the amount of solid will be increasing. So when we are going below the S, the amount of liquid will be goes on decreasing and the amount of solid will be goes on increasing. Suppose just below S, if it is 99% liquid and 1% solid, but near about point N we will get the 99% solid and 1% liquid likewise. Okay, so the amount of liquid will be decreasing and the amount of solid will be increasing. So the amount of solid increases, this continues up to N, and where the last liquid freezes to the solid. Here at point N, the last liquid will be just freezes to the solid at exactly point N. Now between S and N, the alloy contains the liquid and solid phase. So in between S and N, liquid as well as solid state we are getting. So whatever the alloy is there, so both the phases we are getting, that is the liquid as well as solid. Now when we will apply the lever arm rule, how we can be able to calculate the amount of liquid and solid, that is the interesting. Now here in this particular diagram, the liquid will be contains in this particular zone. So when we want to calculate the amount of liquid with the lever arm principle, we have to consider about the opposite arm. So here we will consider this will be the lever, okay, that is O to P, it is just a lever arm. So when we are applying the principle of lever arm, how we can be able to apply to calculate the amount of liquid. So when we want to calculate the amount of liquid, that is opposite arm we have to consider, that is OM, and divided by the total arm OP. So this is same, OM upon OP. Similarly, when we want to calculate the amount of solid, here the solid will be present in this particular phase, and when we want to calculate the amount of solid by the lever arm principle, we have to consider the opposite arm. So opposite arm in the sense from the intersecting point to this particular section. Okay, so this will be the opposite arm, that is from point M to P. Okay, MP, or you might be say that 2P, because 2 and M are the same points. So M to P divided by again the total line, that is OP. So similarly M to P divided by OP. So only we have to use the lever arm principle in this particular case. Now what are the actual solidification of the liquid alloy of this type? Consists two processes. What are the two processes? That is the formation of crystal in the metal melt at say at point S. So at point S, the formation of metal, okay, sorry, formation of crystal in the particular melts will be started at just point S. Now just at point M, the growth of crystals. So at point M, the growth of crystals will be there, because when we are talking about any solidification structure, solidification in the sense it is having the crystal structure. So when we are talking about the crystal structure, so when the solidification will be increasing or solid state will be increasing, the growth of crystals will be increasing. So at point M, we are getting the high amount of crystals. Okay. Now the homologations of the composition in the various parts of each crystal. So that is the diffusion between the core and enscapements, and by diffusion between the core and mate. So that is not that much important in the crystal phases. What are the different parts that is included? Now we will talk about the eutectic system. So isomorphous system, it is over now. Now we will just go with the second part, that is the eutectic system in this. Now what is the eutectic system or eutectic point? That is very interesting to understand. So when the eutectic reaction, when a solid solution of fixed composition solidifies at a constant temperature, forms a mixture of two or more solid phase without an intermediate ASCII stage. Okay, so here this diagram obtained for two metals having completely solubility in the solid state and completely insolubility in the solid state. Okay, you understood? So for the liquid eutectic system, whatever may be the two metals are there, so that should be a completely soluble in the liquid and completely insoluble in the solid. Okay, so might be you understood it. So here that liquid, when we are going to cool, we will get the solid 1 plus solids 2. Means here it is, when we are talking about the liquid state, only one liquid state we are getting, that is completely soluble in the liquid. But when we are cooling, we are getting the two solids, that is completely, what we can say, completely insoluble. Okay, completely insoluble. So when we are getting the two solid stage, that is the completely insolubility we are obtaining. So in the eutectic system, there is always a specific alloy known as eutectic composition that freezes at a lower temperature than all other compositions. So at eutectic temperature, two solids form simultaneously from a single liquid phase. Okay. So at eutectic temperature, two solid forms simultaneously from a single liquid phase. So this is suppose a point where we are getting the two different solids. So this particular point is, or this particular temperature, it is just a eutectic temperature. The eutectic temperature and composition determine a point on the phase diagram called a eutectic point. So this particular point, it is the eutectic point. Now we will just go with this particular diagram. So here you can be able to understand. So we have taken, for the sample purpose, we have taken the two metals A and B. Okay, so this is the phase A and D. So when we are just here, only A it is present, this is in the liquid state. Okay, so at this particular stage, the A plus liquid we will get. Here is the eutectic point. So this is the eutectic point. So eutectic of A plus B. Here whatever may be the, in this liquid, A plus B it is present. Okay, A metal and B metal, and when we are just dropping out the temperature, okay, so in this particular zone above this E, so what are the stages that we will see in the next lecture, but only you have to understood here in this diagram, there is A plus L, and below this in the solid stage it will be A plus eutectic. Okay, so below this particular line DEF, the solid state it is there. So in the solid state, A plus eutectic, that is eutectic point. Here liquid plus B, and this is the eutectic point. So in below this eutectic point, the two separate solid we will get, A plus B, and here in this zone B plus eutectic. Okay. So the above diagram, C and G are the melting temperatures of metal A and B respectively. So C, it is just melting temperature of A, G is the melting temperature of B, of metal B. We have just given the name, metal name is A and B. Okay. So by adding both in each other, the melting temperature is lowered and following the curve C and G respectively. So when we are adding both these things, the curve will be follows, that is CE and GE, that is the melting temperature will be dropping. So these curves intersect at point E called eutectic point. So the temperature, melting temperature will goes on dropping, and at a certain stage or one common melting point we will get. So below this we will get the solid state in the two different forms, and above this we will get the liquid state that is in the single form. So this particular point E is called as an eutectic point. So below this eutectic point, when the temperature will be drops, we will get the two different solids, and when we are again increasing the temperature, we will get a single liquid. Okay, so which represents the lowest temperature at which mixture A and B melts. So this is very important. So point E is called as an eutectic point, which represents the lowest temperature at which the mixture A and B melts. And the liquidus of diagram is CEG and solidus is CDFG. So what is the liquidus diagram? That is CEG. This is the liquidus diagram. And what is the solidus? That is the CDEFG. Okay, so this particular line, this is the solidus. Above this liquidus, here is the solidus. So these are the different stages of any eutectic diagram. So these stages we will explain in the next lecture. Only you just draw this particular diagram. With this diagram, we will just come up with the next lecture just to understand the different kind of that stages in the eutectic diagram. So I hope you have enjoyed this particular lecture. Thank you very much for the patience listening.